Okay, we would like now to discuss the Landau big O and little o notation. So basically, many times we write something like here's a wonderful statement that theta of x is O of x. So we use this kind of notation. What this means is that theta of x does not increase faster than a constant multiple of x. So this notation means it's due to the mathematician Landau, and it means that there exists, so the meaning of this is that there exists an m greater than 0, so that theta of x in absolute value is less than or equal to m times x for x large enough. So usually this notation is used when we're trying to approach a certain limit. So in the study of the prime number theorem, for example, we're trying to let x approach infinity. So this means that in a neighborhood of infinity, this inequality will hold like so. Okay, so that's the big O notation. And like I told you, very interesting, and it's a non-trivial result to prove is that theta of x does not increase faster than x. Of course, if you prove the prime number theorem, then that says that theta of x is equal to theta of x increases as fast as x tends to infinity. Theta of x over x tends to 1. But still, this is an interesting thing to see. And we have the little o notation. So the little o notation is that, let's say, a function f of x is little o of phi of x if the limit, again, as you approach the point you're interested in. So if we're talking about then the limit as x tends to infinity of phi of x of f of x over phi of x is equal to 0. So in other words, this would mean the little o notation would mean that the inequality that we see here is true for any arbitrarily small m as x tends to infinity. So it can be true for any small m. So for example, just to give a trivial example, x would be O of x squared. Okay, this is why it's because x over x squared, the limit of x over x squared is 0 as x tends to infinity. Or another interesting example that we could give here is that, remember, the prime number theorem is equivalent to the limit as x tends to infinity of theta of x over x being equal to 1, which, of course, this means that the limit as x tends to infinity of theta of x over x minus 1 should be 0. And this is equivalent to say that the limit as x tends to infinity of theta of x minus x over x is equal to 0. So you might argue now that the prime number theorem is equivalent to saying that theta of x minus x is little o of x. Okay, so this quantity theta of x over x oscillates in a way which establishes it to be infinitely smaller in general than x. So we can see that certain limits can be translated to this kind of results. And the big O notation usually allows us to bound roughly a rate by which a function increases. The little O notation tells us that two such rates are one is less than the other, pretty much. So this is the big O and the little O notation that we use very, very often in analytic number theory. And that's all. Thanks for watching.